Hi. In today's video, we're going to be talking about how molecules are not static, but in fact they are constantly in motion. Not only molecules, but bonds. So if you remember that Morse potential with the little U shape at the bottom, the molecules, the atoms are constantly vibrating, and molecules are constantly rotating and vibrating. And so if we look at this molecule as drawn, we have ethane, and ethane is simply C2H6. And it's a good way of starting our ideas of conformational analysis. So as drawn, you can see that these two hydrogen atoms are on the same plane, and they're in the same plane as these two carbon atoms as well. So in order to understand conformational analysis, we have to really think about other ways we could draw this molecule. I'm going to highlight these as blue and red just so we can keep track of the bonds moving forward. If we rotate about the red bond, we can see that now we have put this hydrogen atom in the back, and the hydrogen that was in the back is now in the same plane again. And again, if we highlight these with red and blue, we can keep better track of the atoms. I recommend if you are doing this at home, you can make a model, and we'll show a model kit in just a few minutes here. So the way that we like to look at conformational analysis is using something called a Newman projection. And so in order to do a Newman projection, we have to look down a carbon-carbon bond, or down a atom-to-atom bond. And this little symbol here means it's an eyeball. And the way you can think about this eyeball is that it's part of a face, so there's an orientation associated with it. There are atoms that are higher versus lower, and again, if you're thinking about this as your face and looking at a model kit, it'll help you to orient how this Newman projection works. So the Newman projection is a system of, it looks like a Y if you're looking directly down this carbon-carbon bond, and this particular hydrogen atom would look like it was on the right side of the molecule if you're looking down the carbon-carbon bond in this direction. The way we represent the carbon atom in the back is with a circle. So that the convention is that the carbon atom in front has an intersection in the middle of the Newman projection, and the carbon in the back is drawn as a circle. So if we look at this molecule on the right, we can do the same thing and recognize that there's this carbon, this hydrogen is this hydrogen, this hydrogen down here is this hydrogen down here, and I'll again color code it to help you keep track of what's going on. So again, there's the blue and the red in the back. And now let's look at how these two structures can interconvert. And so what's happening between these two structures is again a simple 60-degree rotation. And so if you were to rotate, grab onto this red hydrogen atom and rotate it 60 degrees, you would now have this hydrogen atom in the bottom position, and you would move the hydrogen that was here up to here. So you're just kind of rotating it counterclockwise in this case. It's important to recognize that these orientations have names as well. When we're in this orientation where the atoms are eclipsing each other, just like the solar eclipse or a lunar eclipse, we call this eclipse. And in this orientation, when they're all as kind of as far away from each other as can be, we call that staggered. So next we're going to look at butane, and this is where I really want you to make a model, and I'm going to make a model as well. So I'm going to highlight that this model took a little while to make, and it's a little bit complicated to put all these carbon-hydrogen bonds on here. And so what I would recommend instead is to truly use a model as a tool to help you understand things. And so I like to use color coding. I often use red and blue atoms. Even though the convention is a red is an oxygen and a blue is a nitrogen, I like to use these to keep track of where carbon or hydrogen atoms happen to be on a molecule. So let's do a quick switch, make this model much simpler to look at, and let's highlight some of the coloring. So these two methyl groups, I'm going to highlight one as red and one as blue. And we're going to look at an energy diagram. And the way this energy diagram works is you have energy going up in the y-axis, and along the x-axis, we're going to look at how energetically favorable or disfavorable it is as we kind of take a stroll while moving the bonds, rotating the bonds around each other. So if we were to take this blue methyl group and rotate it 60 degrees, we now have gone from a staggered and a really stable staggered conformation to an eclipsed conformation. And this is energetically unstable, so now the methyl and hydrogen atoms are eclipsing each other. If we now take that blue methyl group and move it another 60 degrees, we now get to a new staggered condition. But this staggered conformation is not quite the same as this original. In this original, these two large groups are as far away from each other as can be. In this new orientation, these two large groups are relatively close to each other, and we call this particular orientation a gauche interaction. And so that is not quite as energetically favorable as having them as far away as possible, but it's much more favorable than having them be eclipsed. Eclipsed is always bad. So now, if we think about the next rotation, we would have a situation where we have the two large groups, the two methyl groups, eclipsing each other. Now, this is the worst possible situation that could happen, and so it is energetically the most unstable conformation. And you can keep doing this around the whole 360 degrees, and I recommend that you practice this on your own. And if you recognize that this molecule has energetically more or less favorable conformations, but in reality, at room temperature, all of these bonds are whizzing around very, very fast rates because these energy differences are actually quite small.